Throughout this semester, we're going to see many different kinds of mathematical objects, and most of them will be what we call a function. So here, we're going to discuss functions and look at some properties of functions and some things we can do with functions. So first, we'll define a function. Definition. A function consists of a set of inputs, a set of outputs, and a rule assigning exactly one output to each input. And in math, there is standard notation for all of these things in the function. Before we get to the notation, let's establish another definition. Well, before that, notice this function definition, there are three parts. A set of inputs, a set of outputs, and a rule assigning exactly one output to each input. And when we're determining whether something defines a function, what we're really going to be doing is looking at whether that rule satisfies this condition. But to ease language, we have this second definition. We call the set of inputs the domain of a function, and we call the set of outputs the range of a function. Oh, I should have mentioned, right here there is a glare. In the past I've used a few lamps scattered throughout the room to light this because the overhead light does create a glare. But I'm just going to, this time, try to avoid this glare. You might notice there's a blue circle around where the glare is, so I do believe I will be able to avoid that. Now, let's set some notation, and this will be consistent notation throughout the semester, standard notation. We'll let x denote an element of the domain, meaning x will be an input of our function, and y will denote an element of the range of a function. So, right now, we have x's and y's, and a rule assigning exactly one y to each x. There are many ways we can denote a function. Well, there are many ways we can denote this rule. We'll use mainly one way. Right here I'll introduce two ways, but well, first will be just to look at this third part of the definition in a little more detail. But after this, we'll pretty much use the graphical interpretation of the function, which we'll see in our second example. But before that, let's do our first example. Example, discern whether each defines a function. And here we're going to use our standard notation, x's and y's, and I'm going to arrange them in a table. And I am pretty sure this example will be the last time I use this notation. So let's do some numbers. Now, these don't have to be, to define a function, you don't have to actually use numbers. We'll use numbers for all. Let's do 0, 1, 2, 3, 4. Those are some good numbers. How about 2, 1, 7, negative 3, 9. There are going to be three parts for this first example. Part A. So we have this set of inputs, our x's, this set of outputs, and this juxtaposition will define this rule. And we have to figure out whether this rule assigns exactly one output to each input. Well, we have input 0, input 1, input 2, input 3, input 4, and each one of these inputs does have exactly one output. So I'll say yes. And also to establish some language we'll use. Yes, instead of saying yes, this does define a function, let's say that more in terms of our notation. Yes, y is a function of x. Language we will be using throughout the semester. Let's look at another. Which one do I want to do second? There are three of them. Okay, I want to do this one second. X, y. I forgot which one I want to do second. 0, 1, 2, 3, 4. And let's do 1, 7, 3, 3, 5. So we have 0, 1, 0, 1, 1, 7, 2, 3, 3, 3, 4, 5. So we have set of inputs, set of outputs. Does this rule assign exactly one output to each input? Well, does it? We have input 0 going to 1. Input 1 goes to 3. Input 2 goes to 3. Input 3 goes to 3. I think I said 1 goes to 3. 1 goes to 7. Sorry. 2 goes to 3. 3 goes to 3. 4 goes to 5. So each of these inputs does have exactly one output. Input 0, one output. Input 2, one output. Input 3, one output. What would prevent it from being a function is if there were an input with more than one output. So I'll just say yes here, y is a function of x, but I'll just say yes because who wants to write the same words twice right next to each other? And let's do a third one. You may notice this is a white eraser. Have you ever seen a white eraser before? Well, I have. This is a Mr. Clean Magic Eraser. Works pretty well on these boards. So let's, again, discern whether this defines a function. I told you there are 3 examples. Here's the third one. First 2 are yes. You might suspect that this one will turn into a no. Too many 3s here. Let's get rid of that 2 also. So we have 0, 4, 1, 7, 2, 1, 3, 5, 3, 8. Does this define a function with our x and y notation as set in what I just erased? Well, we have inputs, we have outputs. Does the rule assign exactly one output to each input? Well, input 0, I see only one output for input 0, so that's okay. Input 1 has only one output, 7. Input 2 has only one output, 1. But notice here, input 3 has 2 outputs, 5 and 8. So, no, this does not define a function. Why? I'll just say, in keeping with the language in that definition, I'll say input 3 has multiple outputs. Multiple, more than one output. Input 3 has output 5 and output 8. So that does not define a function. And notice, if you compare B and C, and in part C, what went wrong was having an input with multiple outputs. And in part B, it didn't go wrong that we had an output with multiple inputs. Definition of a function says each input has exactly one output. So this is one way we can denote a function. Let's look at another. We can also describe functions as subsets of the Cartesian plane. Now, what is the Cartesian plane? Well, it does have a formal definition, but with our notation, x's are going to be our inputs, our domain. Y's are going to be our outputs. And pretty much every function we look at, it might be every function, it will be every function we look at, will have domain some piece of the real number line and range some piece of the real number line. And the Cartesian plane provides us a way of describing that relation. The real number line can be denoted with a line going off to infinity, going off to negative infinity. And here, a horizontal axis, the x-axis, is going to denote, is going to stand for our domain. And, the domain is going to be a piece of this horizontal axis. The y-axis is going to denote our outputs. And since we're going to have only numbers, the x number is going to tell us how far in the positive direction or how far in the negative direction we go horizontally, and its corresponding y value will tell us, given that x value, how far up and how far down we go. Now, technically, these lines do go off to infinity. But, you know, that's and drawing the arrows, that's a lot of extra writing that isn't completely necessary. And also, so I just unplugged the lamp with my foot back. And also, writing out the x and the y is sometimes inconvenient because it's a standard notation that everybody's used to. So, commonly, I'll just write it like this, assuming these are x's, assuming those are y's. But example, here we're going to have 3 examples again. But discern whether each defines a function, keeping in mind our definition of a function, inputs, outputs, and a rule assigning exactly one output to each input. So here, we have a Cartesian plane. Let's do one like this. Now this definition up here, it says, well, this remark, functions can also be described as subsets of the Cartesian plane. Well, right here, this line, this squiggly line, does define a subset of the Cartesian plane. That's not all of it, it's a piece of the Cartesian plane. Does this define a function? Does each input have exactly one output? Well, if you look at this, there are many inputs to check, but you can look at a couple and generalize. Look at input there, wherever that input is. I'm not going to mark off a number, but this input, notice, does have exactly one output, that y value up there. What about this input? I'll mark it with a squiggly line. That input has that corresponding output, whatever that y value is. And notice, any input you choose here, you go up to the piece of the squiggly line defined at that input. You'll notice there is exactly one output. So yes, that does define a function. It defines y as a function of x in particular. In keeping with the language from our last example. How about this one? Well, I didn't draw one yet. Let's do this. Something like that. Well, inputs and outputs, rules on exactly one output to each input. Well, what if we look at this input? How many outputs does that have? Well, you go to the function. This y value up here, whatever that y value is, its output. There's only one. If you choose, let's go in the negative direction. If you choose input over here, you'd have an output somewhere up here. Well, you'd have a part of the function somewhere up there, corresponding to output up here. Only one output. But what if you choose one of these here in the middle? Let's use a different color. I have a blue marker somewhere. Notice here, choose this input. This has this output, whatever that y value is. This output, whatever that y value is. And this output, whatever that y value is. So right here, no. This does not define a function, since this, all you need for it to not be a function is one of the inputs to go wrong. In the definition with the example of the chart, all we needed was one part to go wrong. Here, this does not define a function, since this input, maybe I'll say this input, that line should go to the word this. So I'll say no, since this input. Now I don't have any numbers here. We don't really need to call these numbers yet. This does not define a function, since this input has more than one output. I should probably say multiple outputs. I'll say has more than one output. Now I'll say multiple outputs. Because that's what I said in the first example. So we needed an input to go wrong. That input did go wrong. Let's look at one more. Let's look at this circle. Does this define a function? Does it define y as a function of x? Well, What happens if you choose this input? All the way over here. How many outputs does that have? Well, notice at this input, it doesn't hit this curve. That's a circle. This has no outputs. Does that prevent it from being a function? No, it doesn't. The rule for a function says that each input has exactly one output. This input here, well, it's not even an input, you could say. The only inputs here, notice, are between those. So this isn't even a potential input. Meaning, well, not meaning, with our previous language, our previously defined language, that x value over there is not a part of the domain. The set of inputs is the domain. Here, the domain is only within this piece of the x-axis. So we have to look in here. What if we choose one of these endpoints of this interval? Well, that does have exactly one output. That's okay. But, I guess I'll use blue again since I used blue in part B. But, that input and any other input you choose inside that interval, within that interval, notice, has multiple outputs. So this also does not define a function. No, since this input has multiple outputs. And sometimes I get a little lazy with writing, especially when I'm writing the same sentence twice. But all we needed was an input which had multiple outputs, and this does not define a function. But, well, pretty much all of the functions we're going to be looking at can be described in this way as a piece of the Cartesian plane. And looking at these examples, let me erase them a little and then redraw them, because there's a lot of writing on these. We can observe something that happens in these two examples which allows us to determine whether a curve defines a function without going through the input-output argument. What can we do? Well, I'm going to redraw this curve, and I'll redraw that curve. Let's erase this board, because I'm going to write the result here. In math, we have words for large results. A theorem is a large, important result. A corollary is a small consequence of a larger theorem. Theorem. This theorem is going to have a name. But if we want to determine whether something is a function, we could go through the input-output argument. What else could we do? Let's look a little more closely at what went wrong here. We took points here, and these points, well, for it to not be a function, we found a given x value that hit the curve more than once. But notice, at a given x value, well, notice the piece of the Cartesian plane defined for a given x value defines a vertical line. Now again, I should have done this in blue. I guess I already drew it. And notice, an input having multiple outputs, the behavior of the curve when that happens can be captured by looking at how a vertical line intersects the curve. So notice here, we have this vertical line hitting the curve twice. That describes one input having multiple outputs. Here, a vertical line hits the curve 3 times. This input had 3 outputs. So when a vertical line hits a curve more than once, that is going to tell us the curve does not define a function. As long as you stick with horizontal being x and vertical being y, x your domain, y your range. Notice here, in this first example where it was a function, any vertical line you chose hit it exactly once. In particular, any vertical line you chose did not hit it more than once. And this theorem is called the vertical line test. Theorem, vertical line test. And I like the phrasing I wrote in my notes, so I'm going to use that phrasing here. The graph of y. The graph of y. Right there, that's a graph of y in terms of x. I'll just say the graph of y defines the function if and only if each vertical line intersects it no more than once, I think is how I wrote it. Okay. Each vertical line intersects the graph no more than once. So notice it says intersects the graph no more than once. That actually takes care of our a potential restrictive domain argument. With that statement, if a vertical line hits it 0 times, that doesn't prevent it from being a function. Notice here, every vertical line intersects exactly once. That's okay. Notice here, some vertical lines intersect exactly once, but defines a function if and only if each vertical line intersects no more than once. So all you need is a vertical line hitting it more than once to screw it up. Here, vertical line hits it 3 times, not a function. Here, you can find a vertical line that hits it 2 times, not a function. Now, in that, in the statement of that theorem, the vertical line test, there is some logic that you may not have seen before. In the middle, it says if and only if. What does that actually mean? Well, first, I'm not going to test you on the logic of if and only if, but in math, if and only if is used to actually describe 2 results. Notice in this sentence, there's something before if and only if. The graph of y defines a function. Notice in this sentence, there's something after if and only if. Each vertical line intersects the graph no more than once. Those by themselves are 2 potentially separate concepts. Those are describing they're describing 2 potentially different things. If and only if in math tells you those 2 things are logically equivalent. The graph of y defines a function is exactly the same as each vertical line intersects its graph no more than once. Now, first I said there were 2 statements. What 2 statements are there? Well, it can be turned into 2 if-then statements. If the graph defines a function, then each vertical line intersects no more than once is one of the 2 if-then statements. That is true with this language. If the first thing, then the second thing. But it also says if the second thing, then the first thing is true. So if each vertical line intersects no more than once, then the graph defines a function. So again, I'm not going to test you on the logic of if and only if, but it is useful to know. We'll see it a couple times this semester, and as you take more math, if you take more math, you'll probably see if and only if show up. It's important to know, at least in the back of your mind, that if and only if means these 2 things are identical logically. So right here, we can tell we have a result which allows us to figure out when we have a function. But let's look at a few important functions. We're going to look at the graphs of 9 important functions to know. Now, we have the notation for the Cartesian plane in terms of x's and y's. When it does define a function, well, this curve up here could be described as y equals x squared. But when that does define a function, to remain consistent with function language, we're going to say f of x function of x equals x squared. And this f of x is going to give us our y values. So here, this curve, y equals x squared. Notice again, I'm not labeling any points. I'm just, for now, we have a curve, looks like that. Notice this goes through 0, 0, grows up on that side, grows up on the other side. Here, f of x equals x cubed. Notice all of these 9 that we're going to do are functions, vertical line test. This one grows up in the first quadrant of the Cartesian plane, but in the third quadrant, since negatives cubed are still negative, it'll go down. It still goes through 0, 0, because 0 cubed is 0. Here, in these first two, notice the domain was all of the x-axis, because you could put anything into those functions and get something out. Here, notice the domain is only 0 to infinity on the x-axis. Here we have the square root function. F of x equals square root of x. Starts at 0, 0, goes up like that. Here we have the absolute value function. The absolute value function, a little more on that in a few minutes. But the absolute value function goes through 0, 0, goes straight up on a line in the into the first quadrant, and also at 0, 0 goes straight up in that negative line into the second quadrant of the Cartesian plane. Absolute value of x. And we denote that with x with 2 vertical bars around it. So there we have 4 functions. And throughout the semester, we're not, here I'm not going to say everything we need about functions. Certain things we are going to, in a few weeks, we'll describe some of the other things we need. So there is more I could say about each of these, but as the semester goes on, I'll say more about them as we need it. But for now, let's just get used to what these look like and what we're going to do with them. Fifth one looks like this, a piece in the first quadrant like that, kind of hugging both of those axes, and the same thing going on in kind of the opposite direction down here. And one of those things I'm not going to formally define now, I'll formally define it, I believe week 2 I put it, are asymptotes. This one right here, f of x equals 1 over x, looks like this. It does have a vertical asymptote and a horizontal asymptote. More on that later and next week. Next, a similar graph. Yeah, maybe. Yeah, that's okay. Yeah, okay, maybe I should. This. Sorry, that squeaked. This does kind of look, more curvy like that, and similarly down there. Probably should have drawn it out. Here, it's a similar situation, but we're going to put that in the second quadrant by squaring. F of x equals 1 over x squared. We're going to see these two curves a lot when we get into calculus next week with limits. Vertical asymptote, horizontal asymptote. Again, more on those in a moment, but for now, that's what that function looks like. Well, both of those functions. Notice both of them have domain everything except 0. And you can see that with the graph. You can also see it with this fraction and this fraction. You can put anything in there except x equals 0. That'll give you a 0 on the bottom. 3 more functions. Yeah, that'll fit there. So later this week, well, you might be viewing this after this week, So if you're viewing this after our Wednesday meeting, we already talked about trig. If not, we're going to talk about trig on Wednesday. Right here, we have the sine function. We have a graph of the sine function, y equals sine of x. And what is important to know about this? Well, the largest it gets is 1. The smallest it gets is -1. And it waves between them, and then it eventually repeats itself. Sine repeats itself. I'll just mark off that x value. Repeats itself at 2 pi, and it keeps going. So it'll keep doing this, curvy, wavy thing. Next, I'll move that over a little. Next, we have the cosine function. Looks similar. It is similar. It is the sine function, but shifted over. It's a lousy curve here. That's a little better. We have the cosine function, which is the sine function shifted over a little, but it is its own function also. It's also between 1 and -1 is the lowest it gets, and it also repeats itself after it gets 2 pi. And finally, the 9th important function to know is the tangent function. And again, all 9 of these are functions that have vertical line tests. The tangent function is technically defined as sine over the cosine. And because of that, you are going to have asymptotes. But tangent function looks like this. And again, we're going to talk more formally about asymptotes next week. For now, we're just going to keep track of them for what we're going to do next. Meaning, for now, it's important to know them for what we're about to do. Tangent function, that's supposed to look like the same thing repeated 3 times. Maybe I should actually make it look like that. Yeah, I'll go ahead. Same thing repeated 3 times. And it keeps going on. This will keep going on in this direction, keep going on in that direction. It'll have these things we call asymptotes at pi over 2, at -pi over 2, and it starts repeating itself every pi units. So right here we have 9 graphs to know, and throughout the semester there are things we'll do for which it'll be helpful to have some of these graphs in mind. So let's do one thing with them now. We can use these graphs to create graphs of more functions using transformations. And I'm not going to formally define the transformations. I think they're best seen using an example, using examples. So let's do 3 of them, or 2, or however many we're going to do. Yeah, let's do 3. I'm going to erase these. Sorry, my magic eraser is squeaking. Example. Sketch each curve using graph transformations. And what is a graph transformation? Well, we'll see all of them that we're going to see as we do these. Let's do 3 will work. F of x equals 2, absolute value x minus 4 plus 7. b. F of x equals 1 over x minus 2. Now, let's make it plus 2. C. F of x equals, how about negative 1 over x minus 3 all squared. We're going to sketch these with graph transformations and illustrate graph transformations in the process. Because again, I find graph transformations, formal descriptions, much more complicated than thinking through them using the graph. What do I mean by that? Well, let's do part A. Notice here, lots of numbers. 2x with x minus 4 plus 7. That's 3 numbers. That's a lot of numbers. But what kind of function is it? It has absolute value of x minus 4. We would expect this to look kind of like our absolute value function. So let's start with that. So let's start with f of x equals absolute value of x. How many am I going to need? 1, 2, 3. Yeah, I guess I'll fit this on the board somehow. So let's start with absolute value of x, which looks like a big V, like that. Great. What is the first thing that happens to this x? First thing that happens to this x is this negative 4. Now, what does that do? Well, what does it do? It shifts it over 4 units. In which direction? Right. Why? Well, I'm going to draw the second one here, third one up there, and the fourth one down there. So what are we going to do? First, we'll deal with that negative 4. How can we do that? Well, I like to keep track of a certain part of the function and then drag the rest along with it. Here, I like to keep track of this origin thing. This function goes through 0, 0. Goes through 0, 0. Why does it go through that? Well, it goes through that because the absolute value of 0 is 0 from just looking at that first curve. But notice, x equals 0 happens when what's inside of the absolute value is 0. X equals 0 gives us this corner point. That happens when what's inside the absolute value is 0. When is what's inside the absolute value here equal to 0? When is x minus 4 equal to 0? Well, x minus 4 equals 0 when x equals 4. So what's inside the absolute value here is 0 at x equals 4. Meaning, this point 0, 0 is now going to occur at x equals 4 with this graph transformation. So that corner point goes over here to 4, 0. The rest of the curve is going to go along with it. So that's one way of describing it. Another way of describing it is, this is a negative acting just on the x, so it causes the curve to move to the right. So you could think of it like that. There is in Chapter 1, I believe it's in section 1.2, a chart describing all these graph transformations and the specific rules. But again, I like to, keep track of a point and then drag the rest of the function along with it. What happens next? 2. Where am I going to write this? Yeah, okay, I'll write it up here, but I have to write it a little lower. Next thing that happens to this is it gets multiplied by 2. Now, what does that do to this point 4, 0? Well, that point 4, 0 isn't going to change, because 0 times 0 is still 0. But what does it do to every other point? You take x value here. It has this y value, whatever it is. But this one says take twice that y value. So we have a certain y value, but we want 2 times that. So instead of this x value corresponding to a y value here, it's going to correspond to a y value much higher, twice as high. And that's going to happen for all of these points other than 4. If you just heard a noise, that was a car driving by. Yes, cars don't drive by frequently here, which is nice. So all of these y values for a given x value are going to go up twice as high. That causes this entire curve to kind of pinch in. So notice, this is much narrower than that, because this 2 makes all y values go twice as high. Now, twice of 0 is 0, but for the rest of them, it causes them to get twice as high. It causes them to go twice as high. And now, the last thing that happens is this positive 7. Now, what does that do? What does that do? Well, what happens to 4, 0? I guess I'll draw the plane a little lower. So here we want f of x is this one plus 7 more. What does it do to 4, 0? Well, instead of being 4, 0, it goes to 4, 0 plus 7. We're taking these y values, adding 7. Taking the y values, adding 7. So instead of 4, 0, it'll go to 4, 7. And the rest of these will also go 7 units higher. The rest of these y values go up 7 units, meaning that point goes up 7 units, but the rest of the function gets dragged along with it. So here, starting with our absolute value function, we were able to figure out what the graph of another function looks like. This caused it to shift right. This 2 caused it to pinch inward. And this 7 caused it to lift up. Well, maybe I should say shift. Caused it to shift up. Let's do part B. Part B. Sometimes in these, you can see people drawing like one arrow to the next. And you're certainly welcome to do that. It would have been arrow to the second, arrow to the third, and so on. I'll just draw them like that. Part B, 1 over x plus 2. Well, that isn't one of our 9 functions. But notice, it does look a lot, if you don't see all those numbers there, like that 2, it looks a lot like this curve. I think I drew it above. I think I wrote it above, I should say, in the previous example. It looks a lot like 1 over x. But there's this 2 here. What does that 2 do? Well, for the first one, we kept track of that corner point down at the origin. And we saw how that moved. But for this one, we don't have a nice origin point. You could keep track of another point. It goes through 1, 1. I find that a little complicated. I think it's much easier to keep track of, again, what happens at 0. Here we have nothing happening at 0, but notice there is some nice symmetry around 0. Where does that occur in this function? Well, it occurs when the denominator is 0. When the denominator is 0, we get this vertical asymptote. So, to go from 1 over x to 1 over x plus 2, which we want to do here, let's keep track of where the denominator is 0. Where is this denominator 0? Where is that denominator 0? 0 at negative 2. And these vertical asymptotes, again, we're going to see them more next week. But for now, you can just think of them as, this type of line where the function approaches it, like that. So this thing that happens at 0 is now happening over here at negative 2, because the bottom is 0 at negative 2. The rest of the function, well, this asymptote is shifting over, the rest of the function shifts over as well. And here, maybe I will label, there's our x-axis, there's our y-axis. So here, this positive 2 caused a leftward shift. The positive 2 acting on, the x caused a leftward shift. And let's do part B. Part C. You may have noticed all the times I said left and right, there was a hesitation. I'm very bad at left and right off the top of my head. It takes me a second every single time to figure it out. Let's do part C. Let's make part C a little more interesting. Let's throw a negative 5. I haven't used a 5 yet. So same thing, minus 5, just to illustrate another transformation, make it a little more interesting. If you ignore all those numbers there, we have negative 1 over x plus 3 squared minus 3 squared, all minus 5. But in its most basic sense, this curve is a 1 over x squared with a bunch of extra numbers attached. So let's start with 1 over x squared and work from there. Like with 1 over x, 1 over x squared has this vertical asymptote where the denominator equals 0. So we can keep track of that. How are we going to keep track of that? Well, first thing that happens to x is that negative 3. Don't worry about this negative 1 or the negative 5 yet. Let's just worry about the negative 3 for now. Meaning, let's just sketch this graph. 1 over x minus 3 squared. What does this look like? Well, this vertical asymptote occurred when the denominator was 0. Where is this denominator 0? Well, if the denominator is 0, when x equals 3. And the rest of the curve goes along. And these are sketches. You don't have to be too precise, as long as it sort of looks like the last one. Like that vertical asymptote is kind of not parallel to the y-axis. That's okay. What is the next thing that happens to this? Well, it's not the negative 5. The next thing that happens to this is that negative. What does that look like? Well, what happens here? We take this and multiply it by a negative 1. What does that even mean? Well, it means we take these y values and multiply them by a negative 1. We take a y value, multiply it by a negative 1. So something where the y value is up there is now going to go down here. Something where y value is up there now goes down here. And similarly, something where the y value is down here now goes up there. What does all that mean? Well, it means positive y values become negative. Negative y values become positive. So this curve is going to flip from up here to down here. It will flip over the horizontal x-axis. Notice this vertical line. If you flip a vertical line over the x-axis, it's still going to be a vertical line. It's still at 3. But the rest is going to flip over the x-axis, and it'll look like that, flipped over the x-axis. And I guess I'm going to erase this and just draw the fourth one over here. I was going to try to squeeze it over there, but now I can do it over here. So finally, fourth, f of x is negative 1, x minus 3 squared, all without 5. Well, maybe I'll draw that a little lower since I have the room. So here, this negative caused all y values to become their negatives, caused all positive y values to become negative, caused all negative y values to become positive. So it flipped the curve over the x-axis as another car goes by. I hope the recording picks up that a car drives by, so it doesn't sound like I'm just losing my mind. So that flipped it over the x-axis. Last, we have this negative 5. And what does that negative 5 do? Well, it takes all those y values from over here, moves them down 5 units. You take a y value, subtract 5, y value here is now going to go down 5 units. It will shift the curve down. Now, how can we be sure we're flipping it or shifting it down 5 units? Well, take this vertical line, shift it down 5. It's still going to be a vertical line through 3. The rest of it goes down 5 units. So bring it down 5. Now, how can we be sure we brought it down 5 units? Well, this curve also has what's known as a horizontal asymptote, a horizontal line that our curve approaches. It has a horizontal asymptote here at height 0, so bringing everything down 5 will cause that horizontal asymptote to go down to negative 5. And again, for now, all we need to know about asymptotes is that they exist and that these two curves approach them. Next week, we will discuss more formally about asymptotes. So here we have a sketch of this curve. Now, there's one more thing we're going to do right now with these. There's one other kind of function that we can describe, we can sketch using the curves we've already seen. That's called a piecewise function. So let's just do it here. Example. Sketch. Good job spelling sketch. S-K-E-T-C-H. The piecewise function. P-I-E-C-E-W-I-S-E. Function. Wow, can't spell anything. F-U-N-C-T-I-O-N. What's a piecewise function? Well, piecewise function is defined in pieces. F of x equals what? Pretty good bracket. What do we have? Let's see. Let's do x cubed if x is less than 0. And what else do we have? cosine x, I guess we haven't seen that one. Let's do this. If x is less than or equal to 0, and let's do 1 over x if x is greater than 0. So sketch this piecewise function. It's defined in pieces. It's defined to be x cubed for a domain, well, for a piece of the domain. It's defined to be 1 over x for another piece of the domain. So how are we going to do this? Well, we can do it in one graph. I'm going to, for this one, just illustrate it in 3 graphs. So let's do recall. The graph of x cubed looks like this. There's the graph of x cubed. Recall also the graph of cosine x. Looks like this. Cosine x looks like that. And it keeps going on. But we want the function, which is this over here, and, oh, cosine x. Why did I do cosine x? Well, because my first thought was to do cosine and change it to 1 over x. Sorry, I should have drawn 1 over x. 1 over x. Looks like this. There we go, cosine x. There's 1 over x. So this function, this piecewise function, is this for these x values, and it's this for these x values. So what we want to do is piece those together given our pieces of the domain. Well, I have a blue marker, so let's mark off this piece of the function on this domain. Where's x less than or equal to 0? Well, x equals 0 is here. X less than or equal to 0, well, x less than or equal to 0 is that piece of the x-axis corresponding to this piece of that function. X greater than 0, we don't have x equals 0 here. We do have x equals 0 here, so we'll mark that off with a dot, a filled-in dot, to notate that we're not including 0. I'm going to use an open circle. But we want everything larger than that. So we're looking at that piece of the x-axis, and that piece of the x-axis corresponds to this piece of that function. So what we want here is the function which is this together with that. So I'll just say like this. Here's our sketch of f of x. And with these, you technically don't have to draw these, the two pieces, but I am here. You know, it's the first one we're doing. So x cubed over here, we need that piece. We want to include what happens at 0, and 1 over x for this piece. So we're going to take that and put it down here. Here's f of x. And so again, you don't have to draw the two pieces separately like that. You could just draw the pieces together, given that domain restriction. One more piecewise function. So if you're viewing this before our Wednesday meeting, you haven't seen our discussion on lines. If not, if you're viewing it after our Wednesday meeting, then you have seen our discussion on lines. The absolute value function is defined as 2 lines. Well, it's defined piecewise as 2 lines. So I'll just say remark. And we'll see this definition at least one other time this semester. The absolute value function the absolute value function is defined piecewise as follows. of x equals absolute value of x. Well, that's not piecewise. Equals what? Well, it equals this if this. It equals this if this. The absolute value of x equals x if x is greater than or equal to 0, and it equals negative x if x is less than 0. So it is, if you've seen our discussion on lines from Wednesday, it is defined as two lines, and you can piece together the graph of these two lines. But it is defined piecewise. This is the formal definition of the absolute value function. And it does, the first piece looks like this, the second piece looks like this. And notice in this example, they do happen to meet up at 0, 0. In this first one, they didn't meet up. More on that at the end of week 2 on Thursday of week 2, I believe it is. But these graph transformations are important. On the final exam, on every final exam I've given Calc 1 for the last 2 years, I put a question which is substantially easier if you apply a graph transformation. And in my spring semester class, nobody made the observation and made the problem much harder on themselves than they had to. So if you're watching this, on the final exam, there will be something, definitely, where a graph transformation, there'll be at least one thing where a graph transformation will make a future computation much easier. But throughout the semester, it will be important to know, at least have an idea what some of these curves look like. So do practice a couple of these transformations. And again, I like to keep track of the transformation rules just by keeping track of a part of the function, keeping track of certain behavior exhibited by the function.